Hi everyone. So in this lecture, we will discuss about the linting process, which is one of the predominantly used processes in the ASIC design. Uh, as far as the ASIC design is concerned, right? So it is expected that the design is going to have the RTL code written in Verilog or system Verilog, and while processing the RTL code for further stages like design verification and then synthesis process and finally leading towards GDS file generation. So most of the ASIC design undergoes this particular flow. We have the RTL design, then we have the linting, clock domain crossing, static timing analysis, and then you know uh, power aware analysis, etc. In the series of the processes required for proper ASIC design, the linting is one of the important processes because linting is an important step to ensure that whether the RTL design matches the actual guidelines required for developing the RTL design of the digital architecture. There are many commercial as well as open source tools available for linting process, and this linting process in fact is performing a static analysis check on the RTL design to find out whether the design has any violations with respect to the guidelines. We have some guidelines as far as the RTL is concerned. Those guidelines have to be taken into account while we are developing the RTL code. But in some cases, if we violate the guideline, right, and if you are unable to find out the guideline in a bigger RTL codes, it is necessary to apply the RTL code into a lint tool so that the lint tool will ensure whether the design is free from any linting errors, whether the design exactly follows the different guidelines. Therefore, the purpose of linting is to ensure that the design is free from any guideline violation. So, what are the guidelines that we have? The guidelines here are related to the RTL design, in fact, RTL code. Um, so mostly it is not with respect to the functional matching, right? The linting process is not going to be used to ensure whether the RTL code follows the specification. The linting process exactly analyzes the internal signals, then syntax aspects, then from the different block perspectives, especially procedural blocking, procedural blocks like always or initial blocks. So it is more associated towards the RTL writing guidelines and not with respect to any functional checking. In fact, indirectly, the linting process is going to help us in achieving the functionality, but exactly from the specification, writing from the features of the specification, it is not going to check whether every feature of this is satisfied in the RTL code. That is the purpose of that process is with respect to the design verification, because design verification is going to confirm us whether the RTL code meets all the features of the specification. Here, it is going to concentrate on the inference of the latches, whether the blocking and the non-blocking operators are used properly, whether the reset is using the proper polarity, whether the reset is uniform throughout the design. So those aspects are going to be taken care by this linting process. Therefore, it checks the cleanliness of RTL design so that the RTL design follows the actual guidelines. In this process, how the linting process works, this block diagram shows the exact process of the linting. The lint tool, whether it is a commercial tool or open source tool, takes the RTL as the input, RTL code written in Verilog or system Verilog. Then the lint tool takes some rule file, maybe a .sqf file or whatever it may be. The rule file contains the list of rules. There are the rules are written in a particular format, especially if you want to waive any rule, that is also possible in the linting. For example, if that particular guideline need not be enforced, the particular guideline need not be checked meticulously, that can be waived or that can be discarded. In some cases, those rules can be omitted from the lint rule collection. Therefore, the rules are important to ensure that what kind of checking is going to be performed by the lint tool. In fact, lint tool requires two things. One is the RTL code, another one is the list of rules. So there is a possibility to comment or uncomment some list of rules from the file that is needed for adding the rules into the lint tool. It is also an important aspect, in fact. So mostly we would like to use all the important priority rules as far as the linting is concerned. There are different priorities to be used as far as the linting process is concerned. There are some guidelines which are going to produce error, linting error. There are some guidelines, the violation is going to produce some kind of warning in that cases. So we have error or fatal or warning kind of things which is going to in fact compare the severity of the different violations. Therefore, here we are in the process of detecting the guideline violation. The rules are decided by the CAT team. So especially based on the priority of the CAT team, they will ensure whether these guidelines are mandatory, these guidelines have to be meticulously followed, or these guidelines can be waived. So all these things will be taken care by the combination of the rules and the lint rule. So the lint rule, the output of the lint rule is lint tool is going to be a set of a summary which is going to give some messages that will tell which line of the code has which kind of violation. If there is no violation, it is going to give a clean sheet so that the RTL code is completely free from any of the major lint errors. So therefore, linting process is going to ensure that whether the design is free from any RTL guideline error. So in that process, we have many lint tools like Spyglass from Synopsys. Then we have Real Intent, LIDA from Synopsys, then SureLint. These are some of the tools. Even in fact, the very later kind of open source tools can also be used for checking this linting process. The goals of the linting process, as far as the goals are concerned, as we have already discussed, guideline violation catching is the important goal of the linting process. So we are expanding the goals further, aligning with what are the different types of guidelines that have to be checked in the RTL codes. So the first one is it's going to check the basic connectivity issues in the design, such as floating inputs, width mismatch, etc. So here we have categorized the major guidelines that are very important for a proper clean RTL development. Connectivity issues, especially in the case of structural model, we do the component instantiation. When we do the component instantiation, what are the mandatory inputs or output ports to be mapped to the main module? One common module, one component will be instantiated in the main module. Therefore, it is important to map the signals of the main module with the component one. In some cases, if we really miss, if we simply declare especially the instantiation by port name, and if we simply mention the component port name, and if we are not mapping anything with the main signal, then the mapping will be empty. That mapping, if the mapping is empty, then that will create any floating design. So your lint tool in some cases will tell that this input is floating, this is not properly mapped. So in some cases it will tell that this is the lint error or lint warning based on the severity. This should be avoided. And then it also checks the simulation issues in the design, such as incomplete sensitivity list. especially there are different ways to write the sensitivity list, which is mainly used in always blocks of RTL code, especially with respect to Verilog. Always at some level A or B or C or A comma B comma C, there are some signals which are going to be important for the execution of some functionality inside the always block, but they are not included in the sensitivity list. In that case, it will say this important signal which is required for running the functionality has not been included in the sensitivity list, so that will point it out as linter. Then incorrect use of blocking and non-blocking assignments. It is mandatory that the registered processes will not use any blocking assignment operator inside the always block. So we will be mostly avoiding usage of blocking assignment operator inside always block. Therefore, in fact, the design objective can be achieved with the help of blocking assignment operator as well, but it depends on the order of the statements that we write, the sequence of statements that we write. In order to avoid that functional mismatches, it is always preferred to use the non-blocking assignment operators inside the procedural blocks like always. Then in the case of in the presence of blocking assignment operator, lint tool will say this blocking assignment operator should not be used. Then potential functional error, some functional mismatches that are happening because of some array mismatch or other things, it will the lint tool will also be able to communicate us. The possible simulation hang issue or simulation race cases, like if we try to assign multiple values to the same signal inside the same always block, then that may cause some racing condition, that will end up in some kind of unknown values of the signal in an uncontrolled manner. The lint error will be capable of catching those errors as well. And then this lint goal identifies the structural issues in the design that affect the post implementation functionality or performance of the design, like multiple drivers. As I already told you, there are multiple blocks, we have multiple parallel blocks. A particular signal has to be driven only in a single block. The signal can be read in multiple blocks, but the driving should happen only from a single block. For example, if we take a signal A and if we try to assign a value 1 to A, only a single always block or a particular block should assign a value 1 to A. The status of the A can be read for further processes in other blocks, but if a particular signal has to be driven, that has to be driven only from a single always block. If it is driven in multiple blocks, even though we are able to compile it, the result will be unknown. So the result is not the one which we really want. So such kind of errors will also be indicated through the linting process. This goal reports unsynthesizable constructs in the design and code which can cause RTL versus gate simulation mismatch. Therefore, this is also one important thing, RTL simulation and gate simulation. If there is a possibility of mismatch because of the unsynthesizable constructs present in the RTL code, that will also be notified by the linting tool. Then rules in Spyglass lint. So this particular demo will involve a synopsis Spyglass. There are different rules in Spyglass lint which are majorly supported. The list shows the exhaustive list of guidelines that are followed by the linting rule Spyglass. Array rules, like if we have a vector, if all the inputs, all the bits of the vector have to be processes, have to be read, have to be used properly. If we miss some bits in the vector, then that will show as the lint violation. Array rules. Then we have case rules. When we are using a case structure, we should ensure that the case has some default case, or it should cover all the possible combinations. It is naturally mandatory to use any default case so that all the non-specified cases can be covered. In the absence of those default cases, the lint tool will say that this is a violation, this is a linter. Then we have reset rules, like the polarity of the resets. If we try to use asynchronous resets, then all the blocks should follow asynchronous reset. Otherwise, if they are going to follow synchronous reset, they should follow synchronous reset. The combination of synchronous and asynchronous resets in the design is not allowed, is not being allowed. So then that will indicate it as a linting error. Similarly, polarity of the resets. In some blocks, if you use the pass edge of reset, in some blocks if you use neg edge of reset, that is also reset rule violation. In such cases also there is a possibility that the lint tool will give some error. Clock rules, especially it is good to have the entire processes controlled by positive edge of the clock or negative edge of the clock. In some violation, because of the enforcement of some rules, this clock violation may also be notified. The usage rules, then we have tri-state rules, assign rules, function task rules, delay rules. Then we have latch rules. Like if you are writing some if statements, then it is mandatory to have some else condition, so that we can expect a latch free RTL design. Otherwise, in the absence of some else cases, there is a possibility that the latching will be produced. That means there is we can produce some intentional latches, but unintentional latches may be produced because of non-coverage of some cases, like missing the else cases and other things. Instance rules, like in the structural model, if we miss mapping of some crucial signals after declaration of the port names, the instantiation list with port name, but missing the actual proper mapping, then in those cases the instance error may happen through the linting process. Then we have synthesis rules, non-synthesizable construct or synthesizable discarded constructs. Though there, if there are presence of that, there may be a possibility that linting process will give error or warning. Then we have expression rules, multiple driver rules. As we know that a particular signal has to be driven by a single block only. It should not be driven by multiple blocks. Then we have other rules like simulation rules, event rules, loop rules, and the elaboration rules, like that. So these are the various some list of rules that are supported by the Spyglass. Some typical lint targets include unsynthesizable constructs, uh, like if you use some initial blocks inside the RTL code, which has to be basically avoided. In the presence of initial blocks inside the RTL design, it will construct it as a unsynthesizable construct, then it will produce a warning or error based on the severity. Then unintentional latches, unused declarations. If we declare some wire or edge, but if we are not using that, or if we are not assigning anything, any value to the particular internal signal, there is a possibility that the unused declarations may raise for some lint errors. Multiple driver and undriven signals, then race conditions, incorrect usage of blocking and non-blocking assignment operator, wherein the registered processes, procedural blocks will require the use of non-blocking assignment operators over blocking assignment operators. Then out of range indexing, like we have if we have some specified n number of elements in the array, if we try to use n plus element for which the indexing has not been declared, then there is a possibility that the lint tool will give the error. So this is a Spyglass platform. So we have three things. One is design setup, goal setup, and analyze results. So we can invoke this through the command called Spyglass after including the path in the platform, the OS platform. So mostly it is based on Linux. So design setup ensures that the proper RTL file can be taken by the lint tool. Then we have some .sqf files which are rarely used, and based on the inputs from the CAD team, then we can tweak what kind of rules are to be allowed, what kind of rules have to be discarded. Then we have goal setup, where we can specify any kind of RTL, the linting process, the depth of the linting process that has to be applied. Then we have analyze results, where we have the run goal is there. So if we click the run goal, then it will show the summary of this particular output. So with this, we will get into the lint tool, right? So through the Spyglass command, we are getting into this lint tool. Now we get into the design setup, and in the design rules we can add or remove the files. And let us add some files here. uh, this is the first file. Okay. So we can remove the old one. So going to goal setup, there are different possibilities here: lint underscore RTL, lint underscore RTL underscore enhanced, lint underscore turbo underscore RTL, lint underscore functional underscore RTL, lint underscore abstract. These are the various options that we can enforce before running the linting on the particular RTL code. Now I have chosen only lint underscore RTL. It is a basic but very effective lint checking on the RTL code. So this is the analyze result. So three things: one is design setup, through which we are adding the file. We can also add files through this, right? So we have given the RTL file for which the lint process has to be executed. Then the goal setup, we are choosing the lint underscore RTL, and in the analyze results, we are going to run the goal. So goal is going to be lint underscore RTL. Now it has taken the lint underscore one dot b. All the files that are used in this particular demo are Verilog files. So therefore, so now this is going to run the execution of the lint process of this. So once the lint execution is completed, it will show a summary. It will show a summary. If this is completely green, then this RTL code is free from any linting errors. It is free from linting errors. So right now, if you look at the RTL code, it's a simple assign. It uses a simple combinational assignment statement. That means 8-bit input and 8-bit outputs are used as ports here. The two vectors A and B both are having 8-bit space. Now the output B is equal to A of 6 colon 0. So that means we are assigning 7 bits to B. In this case, A of 7 has not been used. The A of 7 is not assigned. So that is not being used. Even though we have declared 8 bits, we are using only 7 bits of A to assign them to B. So in this case, it should produce one lint error, but because of some waiver, this is not producing any error in this case. Moving to next example. So there are different examples based on a different guideline violation. Uh, let's add the next file to do. So removing this old file. So goal setup remains the same, lint underscore RTL. Now moving on to analyze results, running the goal. Running this goal again. Yep. So we have received the report. So here, this is also similar to the example one. We have 2-bit output and 3-bit input. The 2-bit output is assigned with 2-bit input, and in of 2. In is a 3-bit vector where we are using in of 1 and in of 0, but in of 2 has not been used here. This is also similar to the example 1, so therefore it's not producing any error or warning. Moving on to next example. This is a goal setup is lint underscore RTL. Going to analyze results. Yep, this has produced some lint errors. So let us look at the code now. This is a code with a case structure. It uses three different inputs, two scalars, one vector as the input and one vector as the output. Now the sensitivity list has in1, in2, in3 and mem as the elements, and of course the entire design is controlled by in1, in2 and mem, but in3 is not used inside the always block. It's not required, in fact, because in3 the out is not function of in3. We have 3-bit output, so out 0, 4-bit uh, 3-bit output. So out 0, out 1, out 2, all these things are assigned, but there is a difference we can observe. There are multiple violations here. We have one is the default case has not been declared here, so that is what we can see here. W7 here, W71 says a case statement or selected signal assignment does not have a default or others clause. So it is pretty clear that if the default case has not been mentioned, it is a proper lint. It's a guideline violation which will cause the lint error. The case statement does not have a default clause and is not preceded by assignment of a target signal in combination block. That is good. And now a signal or variable has been read but is not set. So in fact, because of this, what happens, the case in3 is a 2-bit input, so we have 0 0 0 1 1 1 is there, but 1 0 is missing, and other possible inputs are also not handled because of the absence of the default case. Here there is a violation because we have signal variable has been read but it's not set, because in fact if you see the mem, right, the mem is read but never set. We can observe here the wire 3:0 mem is there, but we are not assigning any value to it, and in that case also we are using logical ORing, logical ANDing. That is also one of the errors which is raised. We cannot, it is not advisable to use logical ORing or ANDing. We should use bitwise ANDing, ORing or other operations. So it says mem has been read but the wire mem has not been assigned. It's not set with any value like 0 or 1 or whatever. Then we have latch inferred for out. For example, if you take the case of 2B00, only out 0 has been assigned. What is the status of out 1 or out 2 if the in3 is 00? That is not assigned. Therefore, it is incomplete. The out is not handled completely in every case. That is why the latch has been inferred in this case. This is a beautiful example to study many things. Absence of the default case, then latch inference, then we are not setting any value to the wire internal signal, then undriven term like the mem3, mem1, mem0, right? So we are not in fact these things are undriven but loaded input terminal of an instance detected. So this is what driving, I think the second one W123 and last one, they remain the same little bit, because it says that you have to assign some mem value, but in the case of not assigning anything, you should not read it, you are reading it. Both these things are there, so that's why it is producing many linting errors. Moving on to the next example. uh, the next example. Right, running this. Yep. So now this is the code. This is a fourth example. So this uses two registers Q1 and Q2, 2-bit registers as output. Then it has input clock, reset, and 2-bit inputs. So it uses two always blocks. Um, in fact, here these always blocks use the outputs Q1 and Q2. All are using non-blocking assignment operators, so it is not a violation. And one difference that we are observing here is the reset. The first always block uses asynchronous reset. Second is also using asynchronous reset, but the polarities are different here. First block uses asynchronous active high reset. So second block uses asynchronous active low reset. That means passage reset in the first block, neckage reset in the second block. That is being raised as one of the warnings here, lint warnings. Do not use a reset or set with both positive and negative polarity within the same design unit. So it says that if you want to use reset, asynchronous reset we are using here, so that is okay to use asynchronous reset throughout the design. But if you try to use asynchronous reset, either use passage reset or neckage reset in both the blocks or multiple blocks. Here for one block we are using passage reset and another block we are using neckage reset. That becomes a lint warning here. Do not use a reset or set with both positive and negative polarity within the same design unit. So this has been raised by the lint tool as one of the warnings. Moving on to the next example. So goal setup remains the same, lint underscore RTL. Analyzing the results, running the goal. Yeah, this is another example. So here in this example, all the outputs are using non-blocking assignment operators. Then we have two always blocks. One is using asynchronous reset, another one is using synchronous reset. Asynchronous reset is the one which is in which the reset process is independent of the clock, whereas synchronous reset, the reset is dependent on the clock. The second always block, if you see, the reset is controlled by the clock, positive edge of the clock, whereas in the former case, in the first always block, the reset is independent of the clock. So if the because in the sensitivity list itself we can see the passage reset over there. So if reset in the first case, so first one is using asynchronous reset, second one is using synchronous reset, and because of that one lint warning has been raised. So it says asynchronous reset or preset signals must not be used as non-reset or synchronous reset or preset signals. Right, we have asynchronous reset and synchronous reset. In the same example, try to use both as synchronous or both as asynchronous. If you use one particular block with asynchronous reset and another block with synchronous reset, then it produces this type of lint warning. So next example, uh, let the goal setup remain the same. Moving on to analyze results. So this is one example where we have So two outputs, two registered outputs, right? Out 1, out 2, and 3 inputs, clock, in 1 and in 2. So here we are using two always blocks. Block 1 is controlled by positive edge of the clock. Block 2 is controlled by the negative edge of the clock. Even though this may be a violation, this is in fact not being considered in this case because of some waivers. So in this case it is being allowed. It will be the same setup. So this is a code with a single registered output, one clock input and a 3-bit vector as the inputs. Here, yeah, we'll take this example without any assignment. Let's not assign this. Let's comment this and run the goal again. Yeah, now we can see some errors, lint errors here. First thing is, it says a signal or variable has been read, but this is not set. Here it says a variable net of 2 colon 0. So here internally we are using net as a 3-bit signal wire, which is read inside the always block, because out 1 equal to in 1 and net. But net is read here for now out is the out 1 is a function of net and in 1, but the value of net has not been assigned. We have simply declared wire 2 colon 0 net, but the value of net has not been assigned. That's why it says a signal or variable has been read, but that is not set. Next is undriven term, undriven but loaded input terminal of an instance detected. So it says detected undriven input terminal. So this is similar to this. In fact, first and 2 are pointing to the net. Here inside the always block we are using net. We have simply declared it, but we are not assigning anything. This error will vanish if we assign some value to the net, in fact. Then next error warning. This is warning. Bitwise operators must be used instead of logic operators in multi-bit operations. In fact, in one is a 3-bit, net is also a 3-bit, so the multi-bit operation. So it's going to be a bitwise operation only, but because of the presence of logic operators, two and logic and two R's, logic R's, right? So if we are trying to apply some bitwise operation, then the bitwise operator has to be used and not logic operator. That is what it is raised as a warning over here. Use bitwise operator instead of the logical operator in expression. That is line number 6. Moving on to next example. 7. This is next example. Goal setup remains the same. Analyze results. The goal. It has produced some lint errors. This is the code, one clock and one out, right? So clock has not been used here. Then we have clock has been used here, but there is a truncation of extra bits. This lint error is called truncation of extra bits because out one is a scalar, a single bit scalar, but out one has been assigned with 4 bits of data, but the size has 1b 1011, which is not correct in fact, because of the truncation has happened. So that means either only one bit has to be taken. Constant 1b 1011 will be truncated. Similarly, constant 2b 0101, 2b should be only 2 bits, followed by that only 2 bits have to be there, but here we have 4 bits in the case. So both are wrong. 4 is also wrong, 5 is also wrong. So truncation will happen here. How many bits are required? Only that will be taken. Either mostly it will take the LSB, right? So, but these type of declarations have to be avoided because we really know that what is the dimension of the particular signal. According to the dimension of the signal, according to the width of the signal, we have to assign it. Otherwise, lint error will raise. Goal setup remains the same. Analyze the results. Yeah, taking this example, so which is output reg q, input clock, reset and din, right? So we have 3 different inputs and one bit output. So we have always at passage clock or neg edge reset. This is an asynchronous reset. If not reset, q equal to 1b0, else q equal to din. Here we are using blocking assignment operator inside the always block, which has to be avoided. We should use only non-blocking assignment operator. So it is showing exactly the same observation. The blocking assignment should not be used in a sequential block, may lead to shoot through. Blocking assignment q equal to d in used inside flip-flop inferred sequential block. Blocking assignment q equal to 1 b. Both these things are wrong. Statement 5 is also wrong. Statement 7 is also wrong. So we have to avoid this type of lint error. We should replace the blocking assignment operator with the non-blocking assignment operator. Then moving on to the next example. Whole setup remains the same. So this is an example which uses blocking assignment operator, but we have output clock reset and output q. Here if not reset, if reset is 0, this is an asynchronous reset, q equal to 0. What will happen if reset is equal to 1? So the else condition is not given here, therefore it says latch has been inferred. Latch inferred. So they are all intentionally we are not making latch, but unintentional latches only. We try to avoid intentional latches in fact. So latch inferred for signal q in module because of the absence of the else condition. So this can be resolved if we have else condition. Next example. This is an example. Yeah, here we are using initial block inside this. So mostly if you use initial block, we can avoid this basically. We need not use that. In fact, initial block is ignored for synthesis, especially if you are synthesizing this. Initial block will be ignored for synthesis. That's not coming under the linting process. In fact, lint error is an input has been declared but it is not read. We have two registered output scalar, registered output q1 and q2 and input clock, but as initial does not have any sensitivity list, we are not reading anything. So even though we have declared the clock, it is idle. We are not using making use of the clock. That is why it says the input has been declared but it is not read. Input clock is declared but not read. Next example. Analyze the results. Yeah, this is one important example where we have a simple half adder module and that is being used as a component in another program. So HA is a module that has been in the, if you look at the line number 7, so component instantiation is happening there. HA with the component instantiation now port mapping by name, not by the order of the ports. So here we are mapping, port mapping by name, instantiation by name. So dot A we have proper mapping, dot B we don't have proper mapping, dot sum we don't have proper mapping, dot carry has a mapping carry. So in the line number 7 we are not properly mapping some of the component ports with the main module. So the proper instance mapping is not happening because for two of the signals the mapping is not proper, mapping has not been done. That is why it raises an error. So input has been declared but it is not read. This is one error that it shows because of this particular mapping. Input B is declared but it is not read, right? So here we are having input B but that is not read here. Undriven term, undriven but loaded input terminal of an instance detected. This is important error. Detected but undriven input terminal. So in fact the first and two are, first is warning, second is error, because we are declaring the input B but we are not driving it. That is the error. Output port of an instance is not connected. That means sum is not connected. Sum is also empty here. B is also empty here. Some inputs to instance are not driven or unconnected. Input B of instance DUT is connected, is unconnected. This is a error. So if we have to resolve this, so the B should be given here B, sum should be given sum as per this particular list. Therefore the idea is, if any port of an instance is not connected properly, it will produce one lint warning or error. In summary, we have some example, whatever the examples that we have discussed so far. Say not if the elements of array are not read fully, then that may be a possibility that this may produce a error. In this case, some waiver has been added there in the SQL file. Missing cases. The case statement should not have any missing cases. The case statement should have the default case. In the absence of that, it will produce the lint error. Then using different reset polarity, we should refrain from using different reset polarities. All the reset polarities inside the design should be same. If you use passage reset, for all the blocks it should be passage reset. Otherwise, if you are using neg edge, everything should be neg edge. So reset polarity should be unique. Then using sync and asynchronous reset, we should avoid using combination of synchronous reset and asynchronous reset in the design, either synchronous reset or asynchronous reset fully. Then module driven by both edges of the clock. Then this is also one important aspect, that we should mostly maintain that all the edges should be same, either passage clock or neg edge clock. Net is not driven. If you are declaring some net and you are reading the value of the net, but if you are not assigning anything, if the net is not driven by any value, then it will cause lint error. Truncation of extra bits. We should be always aware of the size of the array that we are using. Accordingly, we have to assign the values. Otherwise, truncation of extra bits will be reported. Then blocking assignment should not be used inside the always block. Always we should try to use non-blocking assignment operator that helps us in flip-flop oriented blocks. We should always try to use non-blocking assignment operator, and we should avoid using blocking assignment operators. Then in the absence of else statement in the if will produce a latch, because it will not be able to cover the non-specified cases here. All the possible combinations of inputs have to be covered by the code, otherwise it will produce the latch. If we are using initial statement is widely used for the test benches, which we are not going to use it for synthesis process. But when we are developing RTL codes for which the main goal is synthesis, it should be synthesizable. In that case, we should always avoid the initial statement. Then during the component instantiation, all the mapping, the signals should be properly driven. The instance should be properly connected, whether output port or input port, they should be properly connected. If they are not properly connected, there is a possibility that the lint error will be produced. So in this lecture, we analyzed the linting process with the Spyglass tools. Thank you.